Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Gary Ruggles of Synopsys, who's going to talk today about how to deal with the rising amount of data within the data center. So, Gary, we tend to think about lots of data moving through these data centers, but it's not a consistent type of structure. Each one of these is different. Each one deals with different amounts of data, and the data that they deal with is not always the same, but there are some commonalities here too, right?
Yes, absolutely. Some of the commonalities are certainly the one everybody knows, which is speed or bandwidth. Everybody wants to go faster and faster. We have larger data sets, we have more data. And part of that problem is when we have more data, we have to move more data. We have to get it from compute into memory and back and forth. And we need to figure out ways to do that efficiently. And some of the ways you can do that are involving cache-coherent systems where you don't have to keep reading and writing data back and forth. And so there's several standards that have evolved to help deal with that.
And even if we get to the point where we're doing in-memory type of computing or near-memory type of computing, you're still left after all of this, after you've siphoned off a lot of this data and thrown a lot of this into the trash and said, okay, this is just what I'm working with. You've still got to move some of this stuff around, right?
Yeah, you absolutely do. And I think one trend you see a lot in the high performance computing space and elsewhere is the increasing use and demand for accelerators. One example of that is kind of like the GPU or the graphic accelerator. There's now AI accelerators. There's all kinds of general purpose and even special purpose accelerators. And they're great because they free up CPU cycles. But the downside is, how do you get the data between the CPU and the accelerator? What's the efficient way to do that?
So let's drill down into this a bit.
Sure.
So Gary, what are we looking at here?
It's a summary kind of showing some of the chips that are out there, AI accelerators and other chips, and just highlighting some of the trends we're seeing in the server space for CPUs. There's increasing data, of course, we already mentioned that, and the introduction of low latency and also power optimized systems. Because one of the problems is as we cram more and more compute into a smaller and smaller space, it becomes important to be power optimized. We want to offload some of this from CPUs to accelerators. And again, there's more data movement from IO to memory, from CPU to memory. And so as a result of all this, every vendor is now supporting one form or another of cache-coherent protocols.
This gets really complicated as we start filling out the distance between the endpoint and the data center, right? So this whole edge, this gray zone that people are starting to build out is all about moving that data less distance, and all this stuff now has to stay in sync.
Yeah, that's absolutely right. It used to be, cloud was the thing, and we did everything in the cloud because of all the compute power that's there. But now with a lot of the applications, the latency is becoming a big issue, and the amount of time it takes to get something from your local application up into a cloud with all this compute power and process it and get it back to your local application again is prohibitive. And some of the examples are autonomous driving. You sure wouldn't want to be driving down the road at 60 miles an hour and be waiting for something to process and tell you, whoops, there's a pedestrian standing in front of you, for example.
So how do we move that data faster? What kinds of interfaces do we need, and what are some of the standards that are out there?
So when we really focus on this high performance computing space, there's a few that really come into play the most. Certainly everybody's familiar with DDR, and I think everyone's familiar with how much it's changed over the years, moving from original DDR to DDR2. Now there's DDR5 at 6,400, whereas we used to be at 800 megabits per second. So the speeds are increasing on the memory, which is great, but now and that's the interface to the memory, but I also have to move that data around. If I have an application where I have to go from one server to another, rack to rack, box to box, I start to get into the Ethernet space. And so if you look at this middle slide here, what we're seeing is the kind of speeds that are needed and that we're seeing in the Ethernet space. And we're already at the 400 gigabits per second space, and we're quickly moving to a point where people will start implementing 800 gigabits per second, which is going to drive us even beyond PCI Express Gen 5. And that takes us over to this right-hand side, where you see this evolution of PCI Express and CXL as two examples, since they're so interrelated. And what I'm trying to highlight here is it's shown kind of with a real time scale. So you can see how, even though everybody knows PCI Express has been evolving pretty quickly, but you can see that lately it's been evolving even faster. So if you look at the last couple points here, PCI Express 4, going to 5, and then eventually to 6, these are all rolling out in rapid fire fashion. So like within the last 2 years. So we're right now well entrenched at 32 gigatransfers per second for PCI Express Gen 5, as well as for CXL 2.0.
So where do people run into problem when they're designing these systems? What are the real sources of latency that people have to consider?
And there's really several sources, but if you look at it, you can kind of lump them into these three categories in a high level. One is network, which is pretty self-explanatory, but you've got to move data from one point to another. That could be from my local machine here to a server in the next room. That could be from my local machine here, maybe to AWS, where I'm processing a whole bunch of stuff with, with some kind of Amazon server system or something in between. And then the second one here is storage and retrieval data. It's become a big bottleneck in many cases. Moving data from one place to another is great, but I have to get it in and out of storage. I have to process it, then I have to save it, et cetera. So that media storage, not just how fast I can access it, but even what kind of latency is involved in doing that is a big factor. And then kind of the last one on the list is the processing of data. So the actual compute modules. This is where the accelerators, and here we're talking tightly inside a box. We just maybe have to move data from two processing elements, from a CPU to an accelerator. And we'd obviously like to minimize that data movement as much as possible.
So how does this work in the real world?
Yeah, so there's a great example that I think a lot of people, particularly those gamers out there, will be familiar with, which is the idea of something like a HoloLens or an augmented reality headset or something like that. And if you look at this diagram here, we've got some stages where we're trying to navigate, we're picking up something from a QR code, and we're overlaying something onto a real live video stream and maybe getting to a destination. And if you're doing this in the cloud, as shown in the middle here, you've got some really long delays that come into the loop that really negatively impact the user experience. You have to go, of course, through your local network. You have to somehow then go through the internet to some server. The server has to process the images and maybe make the identifications you're trying to do and then move it back down. And if you look at this example, your total round trip latency could be as high as 100 milliseconds. That's a long time, and it's very noticeable, and it was not the kind of lag you'd want to see in any kind of AR, VR gaming. What's increasingly happening is the move to edge computing. And this is, one way to do this is using 5G to get really high bandwidth and lower latency. But the basic idea is now we're just going into some kind of local system where the turnaround times are much faster. And instead of being 100 milliseconds round trip latency, we could be down in the 1 millisecond, where it's really not going to be noticeable for most applications.
So one of the issues here that we have to deal with is we have all these memories, and we also have to move data back and forth between memories and also between different devices. How do you take advantage of this? What's the best approach?
Obviously, the more we have to copy data and move it around, the less efficient we are. So one concept shown in this diagram here is the idea of some kind of converged memory, where we share memory between something, in this example, an accelerator chip and a cloud server SoC. And we can kind of share this memory between the DDR of the SoC and the HBM that might be attached memory for the accelerator chip. And we can do that in this shared memory space and do it coherently so that we don't have to keep writing data from one chip to the other and back and forth.
So how do you solve these coherency problems? So you've got a lot of them coming up. What do you do about it?
One very simplistic way to think about this is to look at kind of three dimensions of the problem. So the first one is bandwidth. And the nice thing is today we've got lots of standards that are sharing the same really high bandwidth that play in this space. And the example I'm using in this chart is PCIe 5.0 at 32 gigatransfers per second. So it's got the 32 gigatransfer speed. And then as we move from the left-hand side to the right-hand side, you can see as we get up here to C6 1.1, many of your listeners may be familiar with this. And we still have 32 gigatransfers per second, but we've added cache coherency. PCI Express doesn't support cache coherency. It's not made for that. So, and then as we go to the right to this CXL standard, we also support cache coherency, but we've done something else. We've given ourselves a huge reduction in latency compared to PCIe and C6, which are very comparable. So we get the bandwidth and we get the coherency and we get the latency out of CXL. It's one of the reasons that one seems to be taking off for so many applications, although it's not perfect for everything.
So where would you use each one of these? What's the difference?
A lot of folks are familiar with PCI Express, so let's look at that one first. In its simplest form on the left, it's a point-to-point protocol. You have a root port, or sometimes referred to as a root complex, that's talking to an endpoint. And you can exchange data. You have separate TX and RX paths, very fast. That's where we get that high bandwidth. And then, of course, on the right-hand side here, we introduce the idea of a switch. And this is really important. It exists in host processors in the root complex. And the switch allows you to move beyond this simple picture on the left, where we have one-to-one, to something where we have one-to-many. It increases fan out and allows a PCI Express host or a computer to talk to all kinds of devices. It can talk to an Ethernet card. It can talk to an SSD drive. It can talk to a standard SATA hard drive. It can talk to a lot of different things all through this PCI Express bus because of this switch. Then if you look at some of the applications for PCIe, it's been really ubiquitous. It's been the go-to standard for so many things, but it's not really ideal for these kind of coherent systems that have pools of shared memory. There's no coherency mechanism even defined for PCI Express. You can't really manage pools of memory very well. You've got a single 64-bit address space. And the latency, while it's always seemed okay, now that there's some things like CXL around, suddenly it seems really inadequate for some of these applications. It's not nearly as good as we can get from an optimized CXL link. There are some things you can do with PCIe that are unusual, but we've seen them here at Synopsys, which we'd call like a private link, where you kind of jury rig the protocol and stuff some stuff maybe into the header and some other bits that you're going to use to identify where you're going to take a message from one chip to another. But on its surface, it's really not designed for that.
But you still need to support this in your design, right? Because it's one of the standards.
Absolutely. This is your main interface to get out of your CPU and into everything else, almost, right?
How about the other ones?
Yeah, so the other ones, if we go through that table the way it was outlined, the next one I would go to would be C6. And this is an accelerator protocol. It was faster than Gen 4 when it came out. Now it's at 32 gigs, so it's right on par with PCIe 5. So what's different? Well, what's different is it adds a second virtual channel. And that virtual channel is used for coherent messages. So it has the PCI Express messages on this side and the coherent messages on this side. And it's a symmetric protocol, which is kind of neat for certain applications because it means that every chip that's talking to another chip using the C6 protocol is equivalent. They all can share memory the same way, and it allows topologies. If you look on the lower right here, not only can you have the kind we talked about for PCI Express of host to device and switched architectures, but you can also support things like meshed architectures. And these are interesting to certain high performance computing applications, maybe where you have a whole array of accelerators and you want to have all of them connected together and being able to share coherent memory in this large group. C6 is good for doing that.
You have a lot of moving pieces here. Does it always work as well as you think it does?
No, it doesn't always. And that's one of the reasons some of these other standards have started to get such traction. I mean, one of the things we've seen at Synopsys is as our customers have implemented C6 in real chips, they suddenly, in many cases, get kind of a wake-up call that, wow, this latency is much higher than I thought, and my system isn't behaving the way I thought it was going to behave. So if you look at the kind of limitations and the benefits, we have this symmetric protocol. So every chip looks like every other chip. Every chip implements the entire cache coherency protocol and enables multiple accelerators to talk to each other and share data. But a big problem with this approach can be that if your chip that's talking to everybody else does something wrong and implements the protocol incorrectly, it can potentially bring the entire system down because now it's all dependent. You're like what we call the home agent as well as the device. And so the whole system can come down. And the other drawback that we see with this, again, I mentioned it as latency, is the latency similar to PCI Express, and maybe even with a small adder, because if you look at that diagram again, it had the C6 transaction layer on top of the whole PCI Express stack. So you can't get any better latency really than PCI Express, and typically you get a little bit worse. But it's potentially scalable for multi-CPU, accelerator. That's kind of been the attraction, is you can put these large arrays of accelerators into a platform.
So really you need to think about the entire architecture and how your data is going to be moving through this, as opposed to thinking about from the hardware side. It's more, where's the data flowing?
Yeah, so that's a great point. Obviously, if you were just doing some simple large data transfers in your system from host to device, then PCI Express is great for that. If you need to have data sharing and you're going to have an array of accelerators and CPUs sharing large sets, then C6 might make sense. And if you're going to go to some applications where you need really low latency, then it might make sense to move to something like I'm showing here, which is CXL. So what CXL does is it implements 3 different protocols in the one interface. And those are the CXL.io, the CXL.cache, and the CXL.mem. And combining those in different ways creates 3 different device types. And these can all be useful in these HPC data center applications. They all have to implement CXL.io because it's used to negotiate the link, it's used for register access, and it's used for the long data transfers like PCI Express. But in the case of type 1, we implement CXL.cache, and then you can access coherently the host's memory from your device. So if I'm an accelerator guy, or I build a smart NIC or something like that, I can now cache the host memory directly in my device using this. If I implement another protocol, so in this case, I'm implementing all 3, the .io, .cache, and .mem, now I've got a system where not only I can cache the host memory and do that coherently, but the host can reach down and access my memory as well. So if I'm a card, similar application, if I'm an accelerator card or a smart NIC, and I have some, let's say I've got a lot of attached memory, HBM, I may be using that some of the time. I may not need to use all of that all the time. I can make that available to the host, and the host can use that. And that's really useful in these cache-coherent systems. And then the third type is just, I'm only using the CXL.mem. This is essentially a memory expansion device, but this is also very useful, right? When we have increasing demands for memory, these can be plug-in devices, and now suddenly I can have memory on my card that becomes available to the host.
So as you get to CXL and a lot of the world moves to CXL, what happens to the C6 guys?
At first, a lot of folks, and even people within Synopsys, thought this is just the end of C6, because most applications, they really don't necessarily need these large symmetric arrays of processors and accelerators all talking to each other. And they mostly need a CPU talking to an accelerator or CPU talking to memory. And the advantage in latency that CXL has is so significant that it really has persuaded folks to move away from that. But now what we're seeing is a really interesting potential application that kind of combines the best of both of them in some ways. So what it looks like is the CXL controller that has those 3 interfaces. Instead of that, what we do is we take the .cache and .mem, we take them out, and we replace them with this simple streaming interface called CXS, much like we saw in the C6 controller when it was talking to the ARM coherent network. So what I'm showing here is the standard CXL stack on the left with your 3 protocols, the C6 stack with CXS that I just mentioned is kind of a reference point, and then this new thing called CXL with a CXS interface. It's kind of looks like the C6 controller, but what it does is it enables kind of a new kind of interface. And it's not for free. You have to implement more of the coherency logic in order to do this. But what you can do now is take C6 messages and bring the symmetry that comes with that coherency protocol. And you can take them and send them over this streaming interface of CXS. And you can use your CXL controller and the 32 gig PHY. And you can get the low latency benefits of CXL with potentially the symmetry of C6. So this is becoming really interesting. It's being discussed in the C6 working groups. There's a spec variant of this created by ARM to support this. Synopsys announced that our CXL controller supports this interface. And this might be a really interesting chip-to-chip and die-to-die kind of interface to support this kind of more mesh kind of structure.
The interface world is getting very interesting. There's a lot of moving pieces here. We'll definitely stay on top of this. Gary Ruggles, thanks for a great explanation.
Great. Thanks for having me.